All right, so now with this section, I want to look at a common problem or something we have to overcome when we're looking at XPS and AES, and that's surface charge. So as you can imagine, and this is a similar problem to what we see in something like SEM, is that um, we have electrons, these photoelectrons that we're trying to detect, but if they're not fully removed, then we can have a charging effect. Or, if these photoelectrons are removed, we can end up with a positive charged surface as well. And so insulating materials such as polymers and ceramics, as we see up here, can have a surface charging effect. And just the schematics kind of shown here. So we're removing these photoelectrons, and therefore that leaves a positive charge. So if it's not able to ground and redistribute the charge, then we're going to deal with a positive charge. And the repercussions of that is that we can get huge shifts in our peak location. So this is, I believe, carbon. So there's carbon and oxygen and silicon in this material. Well, down here, the bottom one, this is one where we have an example of surface charging. You can see the peak location over here for carbon is 120 electron volts away from where it should be. So there's a drastic effect because the charging affects what those binding energies end up being. So this is clearly something that we have to overcome because the photoelectrons become more and more difficult to remove from the surface. And so, and so the surface potential, that's what we're talking about, the charge of the surface is affecting the work function that we talked about before, right? So I mentioned this equation for calculating the binding energy, and we saw this is the wavelength of the X-ray, this is the kinetic energy of the electron, and then this was a function of the surface and the spectrometer. So by having this insulating material that's hard to remove, it becomes harder to move electrons, becomes positively charged, it affects the work function, and therefore that's what's shifting our materials. For example, a conductive material, the work function is approximately, it's relatively similar at 4.5 electron volts. So that's always a good approximate. So ways that we can mitigate this. The first one, and all machines have this, and you might have noticed in the diagram, I didn't talk much about the various components other than the ones we mentioned, but they're also in the XPS instrument and AES tends to be this electron flood gun. And it's really what it sounds like. It's a gun that basically prepares or makes low energy electrons. So it basically provides a flux of low energy electrons that it fires at the surface. And the function there is to balance the charge of the surface. So it kind of stabilizes that surface potential. Because you can also imagine if we're constantly removing electrons, not only does it change the binding energy of the electrons, it becomes unstable as well. So it kind of stabilizes that. So this is a process known as charge neutralization. And so all instruments will have this electron flood gun, and it's so that we can deal with these issues with surface charging. Even some conductive materials will have regions that need this charge neutralization. So that's one way we can do it. And so back to that same diagram. So down here, the flood gun is off. And so you notice all those issues with charging. And then down here, we notice that the flood gun is on and it's kind of stabilized back to the position. And there's also some optimization that has to happen with the settings. And you can kind of see the peak shape looks a little weird. And so the flood gun, that's something that you would obviously have optimized either with the machine or as you're kind of getting used to using this. So you have to have the correct flux to kind of compensate for the photoelectrons that you're emitted. So that kind of has to be optimized for your settings. And so that's the importance of having this charge neutralization. Another thing that can reduce this issue is actually to use non-monochromatic X-rays. So we've been talking all of this section and all of XRD about needing monochromatic wavelengths so that we know going back to this function here, we know what this is, right? So now we're talking about using non-monochromatic, and the result here is the same. This non-monochromatic X-ray actually does the same thing that the flood gun does. And so what it's doing is it kind of illuminates the window of the X-ray gun and also the vacuum chamber surfaces, and basically causes emission of secondary electrons in that same kind of flux of low energy electrons. So that's one way, but honestly, flood guns are very common. So I don't, there are probably instruments out there, but flood gun is much more common than using this non-monochromatic X-ray.